two-dimensional motion. Now, instead of moving just along the line, we move in two-dimensional world. Here is x, here is y, and our motion is described by vector r. And we already reviewed vectors in our math module, and we can write r in terms of components, in terms of unit vectors. I can write it as r sub x unit vector I plus r sub y unit vector j. And we know, I'll take different color for this, we know that unit vector I, by definition, is along x and has magnitude I, and unit vector j, by definition, has magnitude 1 and is along y. Now, instead of writing it as Rx, I will rename it to avoid too many indexes. I will call R sub x just x. Can we do it? Sure. We just agree on notations. Xi, where x is x component of R, this leg of this triangle, x, a unit vector I, plus Ry will be called yj. Okay, so this is our position in two-dimensional world, and in this video, we will just derive all formulas that we will need to solve problems on two-dimensional motion. This is the position. Now we need the velocity. Velocity, by definition, is dr dt. So I need to differentiate this expression. I differentiate the first guy, dx dt I, and I have to use product rule. I differentiated x times I. Now I leave x in peace plus x. Derivative of I will be 0 because it has constant magnitude and the direction is always along x. Great, we are done with the first guy. Plus dy dt j, and again, product rule, second guy will be 0 because when I differentiate j, the derivative will be 0. At the same time, we know that any vector could be written in terms of components, so it is equal to v sub x I plus v sub y j. And now I compare guys in front of I and in front of j, and we immediately see that v sub x, x component of velocity, is dx dt. And y component of velocity, now I'm right here, y component of velocity, vy, is equal to dy dt. Okay, wonderful. Now we need the acceleration. Here's the velocity. What is acceleration? By definition, acceleration is the derivative of velocity dv dt. Now we need to differentiate the expression for velocity. I take the derivative of the first guy, and I get dvx dt I, and second guy derivative of I will give me 0, plus dvy dt and j. At the same time, we know that A as a vector could be written in terms of components, axi plus ayj. And comparing the guys in front of I immediately see that a sub x is equal to dvx dt. And ay, projection of acceleration on y, is equal to dvy dt. All right, wonderful. Now, what if I'm given the acceleration and I want to find the velocity? What do I need to do? Well, I need to take integral, antiderivative, indefinite integral, or definite integral. Both ways it will work. I will take the indefinite integral of this expression. So I have ax dvx dt, integral ax dt is equal to integral dvx dt. Okay? So antiderivative gives me my function back. It is vx of t plus constant of integration. That's indefinite integral. This constant I will find from the initial conditions. Now, I want to write what is v sub x. V sub x. And I will write it here as our final formula that we will be, let me see. No, I will write it here. What is v sub x, x component of velocity as a function of time when acceleration is given? It is integral of x component of acceleration with respect to time, ax dt. I will skip constant here because this is already indefinite integral. And when I take it, I will generate another constant, and I will find this constant from the initial condition. So constant will be such to satisfy my initial conditions. This is v sub x. I can do same thing with this equation. Take integral of both sides of this equation, and it will bring me to vy as a function of time is integral. I do the same step, just instead of vx there is vy, and here will be integral ay dt. And the last step that we need to figure out how to find the position when we know velocity, okay? So I will look at this equation, and I will take indefinite integral of both sides of this equation. What will we have? Let's do it. I take indefinite integral of both sides of this equation. I will have integral vx dt, integral with respect to time. And this is equal to integral dx dt. What is this integral? It's antiderivative. We know that I will get my function back. X is a function of time plus new constant. Now, what is x as a function of time? I can find it as integral of x component of velocity, integral vx dt, and plus constant. But I will not write this constant again, same reason. This is indefinite integral. It will generate constant, and I will satisfy initial condition by finding this constant. Now I need to do the same thing with y component of the position. I'll do it right here. So this time I will work with this formula. I will do exactly the same thing, and I will get y as a function of time. Y component of object's position will be indefinite integral vy as a function of time dt. Now, when we have all these formulas, I will summarize them right here. So we have definitions, and I will write everything in terms of components. So what do we know? We know that ax as a function of time is dvx of t dt. We know that ay as a function of time is dvy as a function of time with respect, derivative with respect to time. Then vx as a function of time is dx dt. And vy is equal to dy dt. In addition to that, we learned how to find velocity and position if acceleration and velocity are given. So I will rewrite these formulas right here. If we are given x and y components of acceleration, we can find x and y components of velocity by integrating ax. That's what we did a minute ago. Ax of t dt. I'm just writing all these formulas in one place. Vy of t is integral ay of t dt. And then we have x component of position as integral vx as a function of time dt, and then y component of position as integral vy of t dt. So let's number these formulas. What will be the numbers? I will call this 1, 2, 3, 4, 5, 6, 7, and 8. So now we have these 8 formulas for two-dimensional motion. Two-dimensional motion. And I do hope that you will write them and you will keep them in front of you when you solve the problem. So it is two-dimensional motion formulas. And in our next video, I will apply these formulas to a very specific case when acceleration does not depend on time, when the acceleration is constant.